So good morning, everyone. My name is Ábel Sinkovics. There will be the two of us presenting. This is András Kucsma, and we've been working on a utility for C++ template metaprogramming. And this is the agenda for today's talk. So first of all, I will introduce template metaprogramming. I will show you where it is used, how it works, and I will show you how to use this tool to do template metaprogramming or to make template metaprogramming easier or more human doable, I would say. Let me ask you a question. How many of you feels that he's confident in template metaprogramming? He can just do template metaprogramming. I can see a few hands. Okay. How many of you has read about template metaprogramming or looked at it at least once? Quite a few hands. Is there anyone who hasn't ever touched it? Great. So for those of you who have just tried it, the first part will be an introduction to template metaprogramming, so we all know what we're talking about. And after that, and during that, later on, we will show you the tools we have just developed and you can use to do template metaprogramming. But let's start with a simple question. What is template metaprogramming? So different people have typically different opinions about what template metaprogramming is. So let me ask you a question. What do you think template metaprogramming is? Quite a few people said that they are confident in that, though. Does anyone have any idea? Yes?
Moving a calculation or determining of types to compile time instead of runtime.
So the answer was calculating types at compile time instead of runtime.
Or calculating values also.
And there was an extension to that, and calculating values as well. Are there other ideas?
I also like that it's kind of like functional programming because you don't have mutable data.
So there was another idea. It's kind of like functional programming because there is no mutation.
I'd say actually metaprogramming is about generating high-level constructs using the template system.
There was another suggestion saying that it's about generating high-level constructs using the template system. Okay.
Functional embedded language.
And finally, there is a suggestion saying it is a functional embedded language. Yeah, the last one?
Way to get your compiler to his knees.
The best way to get your compiler to break, actually. That's nice. Yesterday we were having a few beers, and I asked the people around the same question, and here are the answers, what you can see. As you can see, that most of the people weren't that specific and technical in answering these questions while we were having beers. But you might spot that there was a professor with us, and his answer is also included. So that's the answer of a professor, and that will be the sort of definition we will be using for the rest of this talk. So when I will say metaprogramming, I will mean that kind of thing. Okay. So let's start with a simple introduction on why we're doing this. Well, on the why question, I suppose there have been talks talking about or showing use cases of using metaprogramming so far. But here is a very short introduction or introductory example. Let's consider a minimum function. It's a C++ minimum function, no template metaprogram so far. It just takes two values and returns the smaller one. And we implement it as a template function so that you can get the minimum of two numbers or two integers, for example. You can get the minimum of two strings, whatever. And the template argument is the type of the things you get the minimum of. And you can just write it as a template function. The problem is that when you use it like this, then the compiler will deduce the type. But if the types are different, then the compiler will complain, saying that I don't know what T should do. So one possible approach for this is saying that, okay, well, let's say that this template function will have two template arguments, A and B, so the two arguments of the min function can have different types. And now the compiler will be happy because the first type can be int and the second type can be double, and life's good. Can someone spot the problem? Yes?
The return type.
Yes. What will be the return type, A or B, or something completely different in this case? And let's assume that we have some sort of a magical template class. Magic happens here. Let's call it, for example, common type. And this class has two template arguments, and we assume that if we instantiate it with two types, then the template instance will have a nested type called type, and that nested type will be a type def of whatever the return type of this function should be. So assuming that we have this, we can implement the minimum function. We can say that, okay, the return type will be the common type of A and B. And this template class will just do it for us. And if we're about to implement this template class, well, the simplest way of doing this is declaring the template class and then saying that, okay, let's specialize it for int and double and say that, okay, the common type of int and double is double. So if our minimum function has an int and a double as arguments, then the return type should be double. And then we can keep writing specializations for every possible combination, which is, well, yeah, one way of doing it, not necessarily the best way of doing it. But we can take shortcuts, though. We can say that if the types are the same, then it will be the return type anyway. In C++11, we got new language elements which we can use to implement this common type in an easier way. And it's even part of the standard library with a variadic number of arguments. So you don't have to do it like this. The reason why I showed you this example is that this common type is a very, very simple template metaprogram. And in this case, here is some sort of a logic, not too complicated, but still not a trivial logic, which says you've got two types, and you should determine the return type of a minimum function. And you cannot hard code this return type into the program because this can be determined when this min function is instantiated.
Can I have a comment?
Yeah.
The previous slide, the template live struct, and inside you use the using. And I think there's a possibility that you can also templatize using now in C++ 14.
Okay, the comment was that this using could be also templatized. Thank you. So, this thing is a template metafunction, and you can use this template machinery to describe the logic that determines the return type of the min function, given the two arguments. And that is basically what metaprogramming is for, to describe some sort of a logic that is executed during compilation. And that is, you cannot hard code the result into the program. So how does it work? Well, you've got the C++ source code. The metaprogram is part of it. And then you give the source code to the C++ compiler. And during the compilation, your metaprogram gets evaluated. And the result of your metaprogram evaluation will be part of the generated object code. So it will affect the object code somehow. Or you might issue compilation errors or warnings if something goes wrong. Well, there was a common saying, usually. So where is this thing useful? Well, here are a few application areas where this thing can be used. Note that the optimizations part from yesterday's talk on expression templates. I'm pretty sure it's not a complete list, though, of what you can do with it. So here are some examples for this for elements from this list. Well, one usage area is simulating language features. So, for example, in C++98, there were no Lambda expressions, but you could, up to some point, simulate it with template metaprograms and template trickery. There were a number of libraries doing this. One of them is Boost Phoenix. Here is an example of what it can offer. let's assume that you've got a vector v, and you want to display the values that are greater than 5 in that vector. And you want to use the for each algorithm, so you step or iterate over your vector using for each. This is where you would put a lambda expression in C++11. But you don't have one in C++98. But with Phoenix, you can write something like, if the argument is greater than 5, then display the argument on standard output. And it looks like normal C++ code. And it is C++ code, but it means something different to the compiler than it means to you. And there is a template metaprogram behind it that converts it to what you mean, so that you and the compiler have the same idea of what this thing should do. Another example that was covered by a completely different talk in this conference is expression templates to do some sort of an optimizations at compile times, or I could put there smart expression templates as well, following that talk. You can use template metaprogramming there as well. And you can also use template metaprograms to parse string literals, or the content of a string literal at compile time. It's useful for implementing domain-specific languages. So here are a few examples. When you want to build a regular expression library, or you want to build a SQL library or a grammar library, then you can just say that, OK, the SQL query will go into a string literal, and a template metaprogram will check it for errors and issue any errors if it finds any. Or a template metaprogram will check this regular expression and let you know if it's a correct regular expression. Or a template metaprogram could just generate a grammar out of this thing. So these are also things you can do with template metaprograms. And here are two libraries you can use to do this. So these were the examples, and let's look at how this thing actually works. And here is the classical factorial example. There is no template metaprogramming talk, I guess, without a factorial or a Fibonacci, maybe both. So here is the factorial for this one. The idea is that you want to calculate the factorial of n at compile time. And the way you can implement it is that you create a template class called fact with an int argument n, and you want to calculate the factorial of n. And the instances of this template class will have a static member called value, and the value of that value will be the factorial of n. So that's the idea. And the way you can implement it is that you say, OK, the factorial of n is n times the factorial of n minus 1. So you use a recursive expression or formula to calculate the factorial. Of course, you need to stop recursion. So you specialize this factorial template class and say that, OK, the factorial of 0 is 1. And this thing will stop recursion. So here is an example of using it. You say that I want to calculate the factorial of 3. And when you do that, the compiler will instantiate this template class with 3 as its argument. And then because of this recursive function call or evaluation call, it will execute factorial again, this time with 2, and it will execute or instantiate factorial again, this time with 1. And these all use the generic form, and when it instantiates factorial with 0, then it will use the specialization. This will stop recursion, and these things will be constant expressions, so they will get evaluated. So that's the basic idea behind template metaprogramming, and it's great for calculating factorial and Fibonacci at compile time, which is something you might use const expression functions for in C++11. But if you want to build more complex template metaprograms, you need higher level abstractions. So these are sort of ad hoc hacks making calculations. One of those, or the most common higher level abstraction, is called C++ template metafunction, or a type function. It is basically a function evaluated at compile time. That could be a sort of a definition of it or an explanation of it. And as every other function, it has an argument list, a name, and a body. And these template metafunctions are implemented as template classes. And the mapping is that the name of the template class is the name of the metafunction. The template arguments of the template class add the template meta function arguments. And every instance of this template class is expected to have a nested type called type. And the definition of that type is the body of the meta function, and that type is the result of the meta function. So this is a function mapping types to types, basically. And in some cases, for example, in the Boost libraries or the book about the Boost libraries, there is also an assumption that the arguments have to be types. So you can only have class or type name arguments for this template class. And I will use that definition. So here is how you can call it. Here is a template meta function turning a type into the const version of it. And here is how you can call it. So you basically instantiate it with int, saying that, OK, I want the const version of int. So this is a strange way of writing const int, basically. But it's good for an example. So now you've reached this point. And you might say, OK, I want to try it out. I want to implement this addConst function. And I want to make sure that this thing returns const int. But the problem is that trying it out is not necessarily an easy thing, because if you write it, then your compiler will not give you a way of displaying the type const int. So you say, OK, I evaluate this thing, but you cannot tell the compiler, OK, show me the result of this. And there is a utility which we have built called Metashell, which you can use to display the result of a template meta function. And you can download it. There is also an online demo. So you can even try it from a browser and run template meta programs from your browser. And you can download binary installers for a number of Linux distributions, for Mac OS X, and for Windows as well. So from now on, I will show you a demo of using it, and I will explain the rest of the things, showing you how to try these things out with Metashell. And during this, I will also show you how I am using Metashell and for developing template meta programs. So you can start it, and you can use similar arguments you would to pass to a Clang or a GCC compiler. For example, it supports include pass. And then what I typically do is that I create a header file. Let's call it fib, HPP. And then inside the shell, you can say include this header file. And then you've included the, well, so far empty header file into the shell. And you can just say, OK, I will try to create that addConst meta function. And say, OK, using type equals const t. And then you have to tell Metashell, OK, reload this header file and reload everything, basically. The way you can tell it is that you say environment reload. And now you've got the addConst meta function. And you can try it out with int. And then you can say that the result of calling this meta function with int is const int. You can also try it with double, for example. And then you can say that the result of calling it with double is const double. So this way you can easily try out your meta programs, and you get an interactive shell you get for other platforms such as Python, Erlang, Haskell, whatsoever. So this is how the shell works. And I've already shown you how to calculate factorial. And then I thought that, well, but there is this definition of meta functions. So this is how functions should look like in template metaprogramming. And I said that, and the arguments of a template metaprogram have to be types. But the argument of Fibonacci or factorial was a number. Yes?
Can you rearrange the windows to be left and right?
Sure. Is it better? Well, it's still at the bottom.
Yeah.
Okay. So, yeah. So I said that the arguments of template meta functions have to be types, but we cannot write factorial or Fibonacci anymore because they take numbers as arguments. So we got to do something about it. And what you can do about it in template metaprogramming is to say that, OK, I will turn these numbers into types. And the way you can do that is that you create a template class. Let's call it int. it has a template, it has an int template argument, and a static const expression int value, which is n. And what is also useful is to say that it has a nested type called type referring to itself. Now I reload the environment, and now I can represent numbers with types. So I can say, for example, int 13, and this type, int 13, represents the number 13. And accessing its colon value, so this thing will give me the value back if I want to unbox it. Well, this is usually called boxing. I box the integer number and unboxing when I get the number back. And okay, I can represent numbers as types. How can I do operations on them? For example, how can I add two numbers? Well, what you can do about it is you can write template meta functions taking two such types and adding them. So you say that, okay, I'll write a template meta function taking class A and B. I call it plus. And I say that the result of this is it will be an integer. And what I can do here is to say that, okay, I unbox the first number, and I add the unboxed second number to this. And I box the result again. Now I can reload the environment and try it out. Well, to make my life easier and to make me type less, I can create type aliases inside the shell if I want to. So I can say that using I13 equals int 13. It is just like writing C++ code. And now I can use I13, and I don't have to type int underscore 13. And I can do the same for 11 as well. So now it's easier to try this plus function out. I can say I want to try 13 plus 11 out, and I can see that the result is 24. So my plus function works. In a similar way, I can create a minus function as well. So it subtracts numbers, and I can quickly try it out as well. And I get the right result. So this way I can create all the basic operations, multiplication, division, and so on and so forth. And well, it's not only ints that I can wrap. So I can say that, okay, I want a boxing type for booleans as well. So I say that, okay, I create a similar type for boos. And I've got a boxing type for Boolean values, so true and false. And I can say true or false. And it just works. Now that I've got ints and Booleans, I can implement comparison operators as well. So I can say that, okay, I will write a meta function checking if one number is less than the other one. So I can say that I create the meta function less, and it will compare A to B. And it will return a Boolean value. Now, if you look at this highlighting in Vim, you can see that even Vim, and so the compiler can get confused. I'll scroll it up. So Vim and the compiler can get confused because of the less sign and the brackets of the template. So I have to put this whole expression into brackets. And now I can say that, okay, let's check if 13 is less than 11.
No, it's a console.
The right side. On the right-hand side of it, 11 should be an I.
Oh, thanks. So it will tell me that 13 is not less than 11. And the other way around, 11 is less than 13. So my comparison works. There is one thing missing for me to, for writing a Fibonacci function, and this is selection. So an if construct. So far, we've created types and operations on types, so operators, basically. We're still missing control structures such as if. And the way you can implement it is you say that, OK, I will create a helper template class. It will have 3 template arguments, a Boolean telling if the condition of the if is true or false, and the true and the false type. And I can call it if underscore C. and then say that it will be true by default, and I can specialize it for false and say that when the condition is false, then it should return the type false. So again, I can try it out, hopefully without typos this time. And I can say that if C true int double, then it returns int. Otherwise, it returns double. So I've got some sort of a selection utility, but it's not a template meta function. So there are two problems with this. Problem number one is that it's not a template meta function because it has a Boolean argument. That's easy to fix. The other problem with this is that what I typically do is not choosing between int and double for Fibonacci, for example. It's rather saying that if the condition is true, then calculate 11 plus 11. If the condition is false, then calculate 13 plus 13. And this time the condition is false, and my result is not the result of this expression, but the expression itself. And to evaluate that expression, I would need an extra type. And what I can do is to create a special version of if, which just selects one of the two arguments, true or false, and evaluates the result. So what I can do is say that I create a meta function that fixes both of these issues, so the bool argument and this evaluation thing in one go. And it has three arguments, the condition, the true and the false cases. And let's call it eval if. And its implementation will be, it will call if and evaluate it. And it will say that it will unbox the condition, and then we'll choose using if C from the two, and then it will add that extra colon type, so it will evaluate the result. And I've got
the Boolean type's not B, and you use it as C.
You're better than the compilers, guys. So now I can say let's say true, and then it will evaluate the expression for me. And there is a way of making the code of the template meta programs a bit more readable. So I'm using here the type of this expression's type. And what I can do is just inherit from this expression, and then inherit the type inside if underscore C. Well, the screen is not too wide, but it makes it readable, I guess. And it should still work. So it still gives the same result, and the definition of the meta function is a bit more compact. So now I got everything. Let's do a Fibonacci, so that we have factorial and Fibonacci in this talk. So we have both. Fibonacci will be implemented as a template meta function. So it takes the number or the argument as a class. Let's call the meta function Fibonacci. And we will implement it with eval if. So we'll say, OK, let's check if our argument is less than 2. We can use the less meta function. To compare it against 2. And then if it's less than 2, then we should return int 1. If it's not less than 2, then we should use a helper meta function that calculates the Fibonacci of greater numbers. So let's call it fibimp. And we can write that helper meta function as well. It has the same arguments as fib. And it will say that, OK, the Fibonacci of n is basically, here goes the recursive formula. The Fibonacci of n is adding the Fibonacci of n minus 1 and n minus 2 together. So the Fibonacci of n minus 1 is Fibonacci n minus 1. And the same way we can calculate the Fibonacci of n minus 2. And since we're using Fibonacci inside Fibonacci imp, the same way as it is the case with normal C++ functions, in template metafunctions, you need to declare your template metafunction before using it. So before Fibonacci imp, you need to declare this Fibonacci template metafunction. And then you reload the environment, and let's try it out. Let's calculate the Fibonacci of 1, and it will be 1. Let's calculate the Fibonacci of 5, and it will be 8. So this is how you can implement Fibonacci as a real template metafunction using the template metafunctions definition. And during this, I've shown you how to use Metashell to do template metaprogramming development, and a few tricks for creating control structures and wrapping numbers. But still, this Fibonacci thing, or typically numerical calculations, are things you should consider const expression for. So I was just using it as an example, as a simple example. And now comes a little technical break as I pass it over to András and give him the mic.
Okay, can you hear me? Great. So, yeah. So what I'm going to talk about now is how to get a look inside the metaprogram, how this Fibonacci works. And we are going to look inside the compiler a little bit, at least what it does. But before we start, I would like to show you a slide I taken from Zoltán Porkolá's presentation from last year. Is the C++ Now conference. He talked about template and tool support for template metaprogramming in general. And he had this slide, which I really liked. So he said that runtime programs, in terms of tool support, have this, this, and this. But compile time programs only have this. So I think after Ábel's demo, we can add the new item here. Okay, so before we get to the demo, I would like to point out a few things which will be important. So of course, in runtime programs, we have functions. In template metaprograms, we call these metafunctions. And since template metaprogramming is a functional language, every function, we only have function calls basically, but every time we call a template metafunction, a new type gets instantiated. And this is what we are going to take a look at, how types get instantiated. Okay, so let's take a look at Fibonacci. And we are going to take a look at how the compiler instantiates the Fibonacci 4. And so I have a question. Who have used GDB before to debug runtime programs? Okay, almost everyone. So a lot of things are going to be familiar for you. So yeah, okay. So we can start the Metadebugger or MDB like this, and you can give the expression you want to evaluate. And it will tell you that the metaprogram has started, and now you have a GDB-like interface to a template metaprogram. So what's going to happen? In order to get the type of the fib int 4, we have to first instantiate the type itself. So the first step in our metaprogram is going to be the instantiation of fib int 4. Now, if you take a look at the implementation here, hopefully Ábel implemented fib in the terms of evalif. And in order to call evalif with these three parameters, we first have to instantiate these parameters, and this is what's going to happen. So we first have to instantiate the less metafunction with those parameters. So this should be the next step in our metaprogram. Now the compiler starts instantiating the less metafunction. So it will, if you take a look at the implementation, it will instantiate A and B and then compare them. So it will instantiate the first parameter. It should be the next step. You can abbreviate comments just like in GDB if it's unambiguous. So we instantiate the first parameter, we instantiate the second parameter. If you don't input anything, the last command will be repeated. So it's very easy to just step through a metaprogram this way. And of course, we will instantiate the result of the meta function as well. So that didn't happen. Anyway. Okay. So now we get to the eval if part, because if you look at the implementation, every parameter is ready to be passed to eval if. So we will instantiate eval if with false, 1, and the helper function, the fibimp helper function. And we will instantiate, hopefully, both false. Yes, now it's really instantiated. And then, since if you look at the implementation of eval if, it's implemented in terms of if C. So we had to instantiate the bool false in order to get the type, in order to get the value out of it. And since it is implemented in terms of if C, now we will call the if C meta function. And no more types fit on the slide, so I'm just going to show you it on the shell. So if C is instantiated, if C will instantiate, since it is false, instantiate the second parameter, which is fibimp4. It will instantiate minus 4 minus 1. And so every type gets instantiated in a call graph or a call tree. And now we got to the recursive call. And the same thing is going to happen again if we would continue stepping through the metaprogram, but this time with 3 instead of 4. But I would like to show you some other things. So in GDB, you have the tool called backtrace, which if you call, you can see how did you get to the current call. And you can see that we called, this is our main function, we called fib4, fibint4, colon type, which instantiated fib4, which instantiated eval if, which instantiated fibimp, which instantiated where we are currently, fibint3. You can also have breakpoints in MDB. Currently, only regular expressions are supported, but it is very good for most applications. And I would like to show you the last step of the recursion. So we're going to break to fib1. And Metadebugger will tell you that the execution will stop on 2 locations, which is logical if you think about it, because fib3 and fib2 are going to instantiate fib1. So let's see if it's true. So let's continue to the first breakpoint. And as you can see, we reached the breakpoint, and now we're at fibint1. And now we can take a look at the backtrace. If it fits on the fly, it doesn't. So you can see that fib4 was instantiated up here by fib3, which is instantiated by fib2, and the first element should be fib1 on the top of the list, but it doesn't fit on the screen, unfortunately. Okay, so let's continue. So it was instantiated by fib2. And if we continue and take a look at the backtrace from the next breakpoint, you can see that it was this time instantiated by fib3. fib3, which instantiated fib1 on the top. Okay, and now we continue. We reach the end of the metaprogram, and the result is printed. Okay, So, yes, this was the demo. Okay, so let's take a look at how this works, so you will understand how we will do everything. So in Metashell, you have the entered C++ code, which includes the environment, that includes the metafunctions, and so on, and also the expression, which you want to evaluate, the compile time expression. This gets fed into Clang, which will compile our code. And this is a special kind of Clang because it is patched with template. What template does is that it will also print a trace of the template instantiation process from inside Clang. So we will get a trace of the template instantiation process, which will be read by Metadebugger. And what Metadebugger does is that it resimulates the instantiation process. So the compilation finishes, compiler is happy, he's done, and now we resimulate the full process. So this means that we have access to the future in some sense. So let's take a look at another smaller. You can evaluate metafunctions from inside Metadebugger as well using the eval function. Okay. Now we've seen backtrace. We have the inverse of backtrace called forward trace, which looks into the future. And let's take a look at it. So you can see on the top that this is where we started from fibint1, which instantiated fibint, as we've seen before, which instantiated less, which less instantiated 1 and 2, int 1 and 2, then less instantiated evalif. Evalif instantiated bool true, and if c, and int 1. And the result is, of course, instantiated by our main function is 1. Also, you can step forward some steps. So if we step forward 3 steps, we should get 1, 2 to int 1, if everything works correctly. Yes. So this is where we are now. You can take a look at the backtrace that we are indeed at the correct location. And you can also step backwards if you want, which is not possible usually in GDB. So you can just step backwards and reach the beginning of the Metaprogram and start all over again. Okay. So, okay, we have some time. So I want to show you another application of Metadebugger. Let's get back to Metashell and create a metafunction. A simple, no, not a metafunction, but a normal function which is a template function. If you put a backslash, you can input multiple lines easily at the end. Oh, sorry. So this should be void foo const df t whatever. And now the problem is that sometimes it is difficult to find out how the compiler will detect the parameters of a templated function if you don't explicitly tell them what it is. So, for example, you can call foo like this. And what t will be? So in this case, it is pretty easy, it will be int. But sometimes it can be difficult to find out. So Metadebugger can help with this as well. So we can just debug the metaprogram. And take a look at the forward trace. And you can see that foo was instantiated with the template parameter int. And by the way, the result type is void because it is void. So you can use this as well. So I think that's all I wanted to show you. I want to extend the slide with one more item with Metadebugger integrated into Metashell. And yes, future plans. So especially in Metadebugger, there's a lot of things are missing. So for example, we can't yet display where the metafunctions are, which would be very useful. This is our top priority right now. Also, currently we can debug crashy metaprograms, so metaprograms which fail with compile time errors. This is just an artificial limitation because template, which was used to produce the trace, also produces trace even if the compilation fails. So it's just only a matter of time and testing. Also, complicated metaprograms can get very long type names, multiple lines or multiple pages of type names and template names, and we don't have a way to display them very smartly yet. Also, there is a guy called Michael Persson, which created a better template, which we have a better chance to be included in Clang. So we don't have to create a special Clang just for this. So we should integrate with him as well. So we are now going to do questions. If anyone has any questions.
How well does your Metashell allow you to debug very complex metaprograms with, for example, types that span more than a screen? Complex nested types. I've worked on a program that had a type that spanned 6 screens just to print a type. And doing that in a debugger, it's kind of hard to even find out what it is or what it's called.
So if you've got complex types, then in the previous slide there was a future plan for making or giving you a way of displaying it. But if the relation between different instances is the complex thing or is the thing you're after, then you can already do it with MDB, as András just showed you. So you can set breakpoints, get to the critical parts, and then look at back traces or look at forward traces to see the logic at runtime of your metaprogram.
Is it possible to introduce some kind of aliases? So, for example, when you're displaying the complex compound type, that you don't write, for example, int open bracket 3 close bracket, that just to display i3, I mean. So, Metadebugger to be able to show i3 and not the complete real expression.
So the basic idea behind this utility is that it resolves these type aliases, because when you're running a metaprogram, if you think about it, in most cases, it ends up in a way that you, at the end, you resolve a type alias. If you want formatted output, it becomes critical when you start using Boost MPL, where they are using tag dispatching, so a vector of int, bool, and double might be a really complex type to display. For that, Metashell offers a formatting utility to say that, okay, when you would display this thing, you should display some other type which is more human readable instead, such as that I13 or something like that.
Yes.
So that way you can do this.
Okay, thank you.
I think this is really awesome. I would like to know if you have plans to integrate this into some IDEs as a plugin, perhaps, where I could, you know, I don't have to specify the include directories, and I could just click on a file and have it debugged or something like that.
We don't have any concrete plans for that, but if you have some suggestions or you may want to contribute to this, then it's more than welcome. The way I'm personally using it is that I integrate it into the build system. So I get a special build target saying that start the shell, and then I can include the CPP files and then play with them. So that's the way I'm using it instead of integrating it into an IDE. So I haven't really looked at it.
Is there a plan to introduce some kind of profiling so you can find out where in your metaprogram you can make changes to make the compile process run faster?
So Metadebugger, or rather templates, provides this kind of information. And but Metadebugger is not aimed to do that because yeah, this is a tool for another. GDB doesn't profile as well either.
So you would need somebody to make a meta
But
profiler.
I think there are tools that exist that already gather the information by template and use it to profile metaprograms. You can look it
thanks.
up.
Just a comment on that. So template, which is one of the components of Ábel's work, provides both time and memory usage information. It basically just creates a stream of data on every template instantiation or every template action. So beginning and end point of template instantiation memorizations. We can take the timestamps, and also you can switch on the memory usage. It's quite expensive, so we don't do this as default. And it just gives you, I think it's 3 formats on XML or YAML and perhaps in text format. So basically that's what Ábel builds on for the debugging information. They just simply don't put the time information because this is mainly for a debugging tool. But as a separate tool, you can use template as it is.
Do you have any idea if there is anything like that template patch for GCC?
I'm not aware of any approach, but we might try to do this.
Cool.
Not the might part in the sentence.
I know I'm a prick, but you have the Fibonacci sequence wrong. Fibonacci 5 is 5 and Fibonacci 6 is 8. You have a off by 1, so the index is wrong.
Fixes to this Fibonacci are welcome.
Thank you. It's really thank you. It's really awesome. I wanted to ask about the combination with macros. Do you have also a way to debug instantiation of macros and then the instantiation of the template that is macros instantiated to follow this? Or?
So for macro, this utility is for templates. It resolves macros, but it will not show you how they are resolved. There is another utility for which there is also an online demo, which is called Pre-Shell. And that's the same idea, but for macros. So you can use that to debug macros. It is based on the BoostWave library.
Okay. Is there a plan to integrate them together with the debugger and so? Or?
There are no plans to integrate them. So if you want to debug the macro part, then the idea is that you use Pre-Shell. And once you're happy with the macro part, then you debug the template part.
Okay, nice. Thank you.
If there are no further questions, then thank you for your attention.